Hello, and welcome to our lecture on the solvents in paint media. In this lesson, we're going to be talking about the different types of solvents that are used to make paints. Now, just one, that doesn't work well, does it? I need to go to slideshow. Hi, and welcome to our lesson on solvents in paint media. In this lesson, we're going to focus on the different types of solvents that are used to make different types of paint. We're going to focus on their different properties and why you would use each of the different types of solvents. Now, just as a reminder, paint is made up of two primary things, pigments and binders. The pigment is what gives it its color, and the binder is what allows it to attach to a surface. The pigments are made up of colored pigments and extenders. We'll talk a little bit more about that in a future lesson. And as far as the binder goes, you have the vehicle, which is what is used to actually make the paint itself, and then different additives which change the properties of the paint. For example, adding in an antifungal agent to make it so that it doesn't grow mold and that sort of thing. Now, the vehicle itself is made up of two different things. The film former, and that's what allows the paint to stick to a surface, and the solvent. And the solvent is what dissolves all the different components of the paint and evaporates away as the paint dries or cures. So, if you remember, when we make solutions, the solvent is the substance that does the dissolving. It's the thing that's found in the greatest amount in a solution. The solute is the substance that is dissolved. And so it's going to be the thing found that is in the lower concentration. So in the case of a paint, the solvent is going to be the thing that is the most prevalent. And then all of these other things, the pigment, the extender, the additives, the film former, all of those will be solutes within the solvent. Now, there are two main types of solvent, two categories of solvents that are used to make paint. We can have aqueous solvents or water-based solvents or organic solvents, and we call those solvent-based solvents. Aqueous solvents are the oldest solvents that have been used. It wasn't until we came along to the Renaissance time that we started using other kinds of things as solvents, the organics or the oils. So with the aqueous solvents or the water-based solvents, we are using water as our thing that everything is going to be dissolved in. Water is considered to be the universal solvent, or it's given the name universal solvent because it's good at dissolving ionic and polar molecules. And most things around are either ionic or polar. Ionic just means that it has a positive or a negative charge as part of it. Remember going back to our discussion of what an ion was. And a polar molecule is something that just has a partial positive and a partial negative. Now, water itself is a polar molecule. If you remember, oxygen is more electronegative than hydrogen. That means it's going to have a partial negative charge on it. Right? And then each of the hydrogens is going to have a partial positive charge associated with it. So anything that is polar, meaning it also has a dipole, is going to be able to form strong interactions with water. The other thing about water is it can form hydrogen bonds. Remember, a hydrogen bond is that temporary attraction that happens when you have a hydrogen attached to an oxygen, a nitrogen, or a fluorine, and you have a hydrogen attached to another electronegative atom on a different molecule. So for instance, if you remember, we defined an alcohol as being some sort of a hydrogen attached to an oxygen, attached to, and I'm just going to use R here. Remember, R stands for the rest of the molecule. All right, so that was our general structure for a molecule that's an alcohol. That hydrogen attached to this oxygen is going to have a partial positive charge, and this oxygen is going to have a partial negative charge. So we can form a temporary interaction between the hydrogen on one and the lone pair of electrons on the other, and that's our hydrogen bond. And hydrogen bonds are extremely weak. But when you have a lot of them, for example, water with itself can form anywhere from, I think it's 1 to 14 is the record number that they've measured, but on average it forms between 6 and 8 hydrogen bonds. Each hydrogen bond itself is fairly weak, but when you have 6 to 8 of them, they start to add up pretty quickly. So the other type of solvent that is used are organic solvents. Now, remember, we did just a brief discussion about organic chemicals, and I just want to kind of rehash that. Remember, organic chemicals all have in common the element carbon. All right? Every organic compound has carbon as part of its structure. If you remember, we said that there was like 118 elements on the periodic table. And if you have compounds or molecules made up of any of the 117 other elements, it would be an inorganic compound. But if you have elements made of carbon, then it's organic. And then if for the comparison and contrast, the inorganic compounds, there's about 1.7 million known, whereas with organic compounds, we're talking over 16 million. Now, organic chemistry is often described as the chemicals or the chemistry of living things, because if something is living, or at one time was living, it's going to have carbon as its structure, or as part of its structure. You see, life on Earth is a carbon-based system. All right, all life on Earth has carbon as part of its structure. So like the chlorophyll that makes a tree leaf green has got carbon. Lycopene, which is a molecule found in things like tomatoes and strawberries. Lycopene has a red color, and as part of its structure, it has a carbon. From milk, we get things like lactose, which is a sugar which has carbon in it. From ants, we get a compound from their shell known as formic acid. You might have heard of Formica countertops. It gets its name because it's got the hard outer shell like an ant. Well, the Formica, the name Formica comes from the Latin word ant. And formic acid is an acid that comes when you grind up an ant. All right, and that has carbon as part of its structure. Now, inorganic compounds, if you remember, are mainly made up of ionic bonds. Primarily, they're ionic bonds. There are covalent bonds present in some of them, but the large majority are ionic. Organic compounds are almost exclusively made up of covalent bonds. And remember, in a covalent bond, we are sharing electrons. So instead of one atom taking both electrons, and we have a positive charge and a negative, we're going to have a sharing of the electrons. Now, on those molecules that I showed you on the previous page, you can have a lot of carbon atoms, or you can have just a few carbon atoms. Chlorophyll A has 55 carbons in it. Lycopene, 40. Lactose, 12. And formic acid just has 1. So we've got a wide variety there. And you remember that we've talked about polymers. Polymers have a huge number of carbons, often on the order of 50,000 or more. Now, when we did our functional groups, we said that a hydrocarbon is anything that contains only carbon and hydrogen. And there were 4 different functional groups that were hydrocarbons. We had our alkanes. Remember, alkanes just have carbon and hydrogen. Wow, I don't know what happened there. But it's all single bonds. All right, so the carbon-carbon bonds are all single. We can have alkenes, where we had carbon-carbon double bonds. We can have alkynes, where we had carbon-carbon triple bonds. Or we could have the arenes or the aromatics. And in that situation, we have carbons in a ring. And we have these kind of alternating double and single bonds. All right? But all 4 of those functional groups just contain carbon and hydrogen. All of the fuels that we use, methane, propane, gasoline, diesel, fuel oil for heat pumps and things like that, all of those are hydrocarbons. Solvents, things that are used for paints or for doing chemical reactions in the manufacturing of drugs or things like that, they're also going to be hydrocarbons. One of the most common solvents used in the chemical industry is hexanes. And hexanes have 6 carbons. All right, so you're going to have carbon with 3 hydrogens on it, going to carbon with 2 hydrogens, to 2 hydrogens, to 2 hydrogens, to 3 hydrogens. All right, so there are 6 carbons total. Now, the thing that we have to remember is that hydrocarbons are all going to be flammable. All right, we've based really our whole economy, the world economy, off this idea that we could burn hydrocarbons. So we can have gasoline, or that we can have natural gas. And so this idea that they are flammable is hugely important. Now, from an artist's perspective, that actually brings some challenges, because that means that anytime we use an organic compound as a solvent for a paint, it's going to be highly flammable. The other thing to note is that hydrocarbons are not soluble in water. All right, and that's going to be a key thing that we talk about throughout this lesson. Oils and water do not mix. Organic compounds and water do not mix. They're going to form 2 layers with each other. Now, the alkenes, and alkynes all go by the generic name aliphatics. All right? And then the aromatics are the arenes. The name aromatic is actually a misnomer today. When these compounds were first discovered, and we're talking like 1700s here, the compounds that are classified as now as arenes all had a peculiar smell about them. And so they were just called the aromatics because they had this peculiar smell. It turns out, when we start thinking about different smells, there's a wide variety of functional groups that give smells. Amines have smells, esters have smells, carboxylic acids have smells. So all of them are aromatic, so to speak. And so we use the phrase arenes to indicate something that's got this double, single, double, single, double array. But you're going to hear those referred to as aromatics as well, because in the traditional definition, they all have that peculiar smell. All right. Now, when we do our nomenclature of hydrocarbons, the name is based off of how many carbons there are. So methane, you hear a lot about methane gas when they're talking about global warming, and like, for example, cows produce a lot of methane gas. That meth indicates that there's only one carbon in the molecule. And don't know, when I say meth there, I'm not talking about crystal methamphetamine or just crystal meth or just meth. That's something completely different. All right. That the meth in the methamphetamine indicates that there's a methyl group, or there's a one carbon branch coming off of the molecule. And so that's not really anything what we're talking about here. The eth prefix indicates that there are two carbons. Prop is 3, but is 4, pent is 5, hex is 6, oct would be 8, 7 would be hept, 9 would be nona, or non, and then 10 would be dec. And once you get to the pent and you start working your way down, the things we're talking about here, the pent, hex, oct, etc., those are going to be the same as the polygon name. All right, so for example, if you have a polygon with 6 sides, that is a hexagon. And so if we have a carbon with 6, or an organic molecule with 6, organic molecule with 6 carbons in it, it's going to be a hexane. All right. So alkanes are hydrocarbons with all single bonds between the carbon atoms. Butane has 4 carbons. You probably run into butane when you're thinking about butane lighters, or the cigarette lighters. Those are filled with liquid butane. Butane at room temperature is a gas, and so within a lighter, they're going to have to actually pressurize it to keep it as a liquid. But you can see it has 4 carbons attached to each other in a row, and each carbon is going to have 4 bonds. So the first carbon here has 3 hydrogens on it, plus then it's attached to the second carbon. The second carbon is going to be attached to 2 carbons, one on either side, plus then 2 hydrogens. All right, so each carbon is going to have 4 bonds on it. Alkenes are those carbon-carbon double bonds. And you can see here in 2-butene, the central 2 carbons are connected by a double bond. All right. Now, the double bond, the first bond that we form there, is called a sigma bond. And the second bond is called the pi bond. The sigma bond just means that the electrons are being shared in a direct fashion, where the 2 atoms are connecting end to end. And the pi bond indicates that the electrons are being shared in a side-to-side fashion. The sigma bond is going to end up being a lot stronger than a pi bond. Then the alkynes are the carbon-carbon triple bonds. And here you see 2-butyne, and you can see that those 2 interior carbons are connected by the triple bond. In this case, there is 1 sigma bond and 2 pi bonds. The first bond between any 2 atoms is always going to be a sigma, and then from there we go to pi bonds. Probably the most common alkyne that you may have run into would just be CH3. Well, it's not CH3. Sorry. It'll be HC triple bond CH. This molecule has the common name acetylene. And if you've ever been around a plumber or you've ever been around a welding shop, acetylene is the gas used for most cutoff torches or for most plumbing torches. That's because that carbon-carbon triple bond has a lot of energy stored in it. And so when you burn it, it burns extremely hot. And so that can be very useful when you're doing things like trying to cut or bend metal. From the artist perspective, where we run into acetylene torches, most is going to be in doing metalworking. When you're doing metal craft, they'll use acetylene torches to either cut the metal or to heat it to a high enough temperature to bend it for things that are too big to just be able to be bent by hand. In lab, you might remember that we did, when we did our porcelain enameling, we did that using a Meeker burner, which is just a version of a Bunsen burners. And those use natural gas as their source of heat. And natural gas is primarily methane. If you live out in the country and you don't have access to the gas from a company, most likely you have a giant tank in your yard, and that's usually filled with propane. Right? Propane is the alkane that has 3 carbons. Now, like I said, there are over 16 million known organic compounds. And it turns out their molecular formulas, where you just list off what types of atoms there are and how many there are fairly unhelpful. For example, if I have something that had a molecular formula of C10H, let's do 22O. There's a lot of different molecules that I can write with that. I can make some molecules that are part of the functional group of an alcohol. I can make some that are ethers. There are probably over 100 different molecules that I could draw that has this particular molecular formula. I mean, even if you just think of something simple, like C4H10O. All right, we could have the 4 carbons, and I'm just going to draw the carbons here and the oxygens, kind of. You have the 4 carbons in a row, each with 3 hydrogens, and then 2 hydrogens, 2 hydrogens. So we could have that guy, or we could put the oxygen in the middle, like that. Or we could draw another alcohol where we put the OH on one of the interior carbons. All right, so there are, I'm not going to just take the time to draw all of the different molecules that are possible here. I'm just trying to give you this idea that there are a lot of different molecules. And this one, being an alcohol, is going to have very different properties than this one, which we said was an ether. Remember that ether is the carbon-oxygen-carbon functionality. All right, and so there's lots of different things that we can draw with that molecular formula. So when we get into organic compounds, we end up talking about their structure and shape a lot. And so when we represent the molecules, instead of using the molecular formula, we're either going to draw out the complete structures like I've done here on this slide, or we're going to use shorthand where we just draw the condensed structures, or more commonly, we're going to draw the line bond structures. So let's look at an example of each of those types. And we'll just start with something that has the molecular formula C2H6O. Now we can put the 2 carbons connected to each other. We can put the 3 hydrogens like this. Two hydrogens like that, then our OH. And so this is ethanol. All right, it's an alcohol because it's got that OH on it. And by drawing out this complete structural formula, we show all atoms and we show all bonds. We see how each of the atoms are connected to each other. In the condensed structural formula, we remove all of the bonds, but we still show how the atoms are attached to each other. So this would be the condensed structural formula for ethanol. So instead of drawing that first carbon with the 3 hydrogens coming off of it being attached to the carbon to the right, we just write a CH3. And then we have the CH2, and then finally the OH. So we show all of the atoms, but we don't show any of the bonds. Now, that means we have to have a little bit of knowledge about how the atoms come together. For example, we have to know that carbon forms 4 bonds, etc., to understand what's going on here. But it makes it so that we can write these molecules a lot faster in a lot smaller space. And using computers, the condensed structural formula is the easiest one to type. And so you run into the condensed structural formula a lot. If you're working with an organic chemist, however, the structure he's going to use, or the way he's going to draw his molecules, is going to be called a line structure or a line bond structure. And in a line structure, instead of showing all the atoms but no bonds, we're going to focus more on the bonds. There are 2 rules for line structures. 1, every time a line starts, stops, or changes direction, there's a carbon. The second rule says that if a carbon doesn't have 4 bonds on it, then all of the bonds not shown are to hydrogen. So the reality here is we're going to eliminate the hydrogens attached to carbons in our structure. So for ethanol, its line structure is going to look like this. Right? So where our line starts, that tells us we're going to have a carbon. When our line changes direction, that tells us we're going to have a carbon. So in this case, there are 2 carbons shown. And if you look at this first carbon, notice that it's only got 1 bond shown. And that's to the carbon next to it. The second rule for drawing line structures tells us that that means that there are 3 hydrogens on this carbon. They're just not shown for clarity's sake. All right, to make it easy to see what's going on. According to our rules for line structures then, how many hydrogens are attached to that second carbon? Well, you see that we've got 2 bonds shown, which means there are 2 hydrogens on that carbon. Note that we do draw the hydrogens when they're attached to some other atom. The only hydrogens we removed are those hydrogens attached to a carbon. Now, organics tend to be relatively non-polar, especially when you compare them to things like water. There are four classes of solvents that are primarily used from organics as paint solvents. The hydrocarbons, and that's where we usually get our paint thinners, and then the two most commonly used solvents are toluene and xylenes. The terpenes, which they're derived from natural products, things like plants, and from the terpenes we get turpentine and then the pine oils. The oxygenated solvents are things like alcohols, ketones, and esters. And then we have the chlorinated hydrocarbons, things like chloroform, methylene chloride, and carbon tetrachloride. Hydrocarbons tend to be the most common solvent found in commercial paints. The house paint forever and ever used xylenes as their solvent. Xylenes aren't used quite as much anymore because one thing we have to remember about all of these organic solvents is they are going to be dangerous. They're all going to be flammable and they are all going to be carcinogenic. Now, because they are organic and we are organic, they dissolve well in fatty tissue. They can cross the blood-brain barrier. That puts a lot of stress on the liver, and they should only be used with adequate ventilation. They aren't joking when they say, when the warning label says only use in adequately vented spaces. It can actually lead to brain damage if you use them in a closed room. So the hydrocarbon solvents, remember, only contain carbon and hydrogen. They are very fat soluble, meaning that they dissolve molecules with lots of carbons very well. Something is a fat if it has a lot of carbons. And like I said, some are carcinogenic. Benzene is not used very much at all anymore for anything because it's so carcinogenic. They add a methyl group to it, and that's called toluene, or xylene has two methyl groups on it. But even those, we are trying to find different solvents to use because all of these guys are carcinogenic to some level. We like things in the 6 to 8 to 10 carbon range because they are large enough that they don't evaporate away very quickly. So you have a little bit of time to work with them. But they are small enough that they evaporate away in a relatively good amount of time. For example, you don't want to use something that's really large to paint your house because the paint's would take a long time to dry or for that solvent to evaporate away. And so you might have a tacky wall that you couldn't touch for 2 or 3 weeks. We want something that you can actually be able to touch in an hour or two. And so we're looking for things that have, in that 6 to 8 to 10 carbon range. The terpene solvents, like I said, are obtained from plants. They mostly contain carbon and hydrogen. The big difference is these guys often contain carbon-carbon double bonds. That makes them a lot more reactive than the hydrocarbon solvents. They are still fat soluble. And the two main categories here are the turpentines. And here you can see on the bottom pinene, which is a balsam. But the balsam is one of the pine oils, but it's a terpene as well. All right. As you can see, just based off our idea of line structures, every time a line starts, stops, or changes direction, we've got a carbon. So here you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, right? But these guys are great solvents for things that are other fatty things, other hydrocarbons. So these guys often get used to clean up from paint. The oxygenated solvents, by definition, have an oxygen. So those are going to contain a functional group that has an oxygen in it, like the ethers or the alcohols or the ketones. Because they have that oxygen, they're going to be more polar. And since they're more polar, that means they're less fat soluble. They're going to have a harder time crossing into the body or being absorbed. And they are often, because they have that carbon-oxygen bond in it, they look more like food. And so a lot of them can be broken down by our body, right? And when something is broken down by our body, it's called metabolized, right? And so these molecules are more readily metabolized, and then they can be excreted. They don't build up in the body like the hydrocarbons do. However, these guys are acute toxins, meaning that if you get a strong enough dose of them quickly, they will kill you. Alcohols like methanol, ethanol, and isopropanol are used extensively. Ethanol is the alcohol that's sold for drinking. But methanol, ethanol, and isopropanol is rubbing alcohol, all three of those are extremely toxic. You drink, for, methanol, ethanol, we're talking, less than 500 mils, and you've hit the lethal dose of it. Ketones, like acetone, are used as fingernail polish remover. Esters, like ethyl acetate, is also used as fingernail polish remover. And all of these guys are acute toxins. The alcohols, methanol, ethanol, 1-propanol, and 2-propanol, are shown here. Notice the methanol has the 1 carbon, ethanol 2, the propanol, I left out a carbon. Sorry, this is the same thing drawn twice. There should be another CH2 there for that to be propanol. And then 2-propanol has the OH attached at that second carbon instead of being attached on the end. The alcohols all have that OH group on it, which we call a hydroxyl group, which allows it to hydrogen bond to a lot of different things like water. And so the low molecular weight alcohols are all going to be water soluble. Methanol, ethanol, propanol are all miscible, meaning you can put as much of it as you want into water and it will never separate out. A diol has 2 hydroxyl groups. The ethylene glycol you see here has 2 carbons, that's where the F comes from, but it also has 2 OHs. When you have 2 OHs on adjacent carbons, they call that a glycol. Ethylene glycol is antifreeze. It's what you buy at the store as antifreeze. Now, these alcohols are going to be polar like water, and so they're going to be able to dissolve a lot of the same pigments that water dissolves. But because they are organics, they're going to evaporate away they're going to evaporate away faster than water. So it makes them a little bit better as a solvent. The halogenated solvents really are not used as much anymore in the art industry or in paints. And really we're trying to get away from using them commercially as well in the chemical industry. The halogenated solvents contain one of the halogens. Remember, halogens are found over in group 7 on the periodic table. That's our fluorines, chlorines, bromines, and iodines. The problem with hydrocarbons is that they are very fat soluble, which means that they can be absorbed into the body readily easily, where they can act as toxins. All right, and since they are non-natural, there's only one halogenated compound even found naturally in the body. They build up in the tissue and can lead to lots of problems like cancer. They are also teratogens, meaning they lead to birth defects. The general idea of these is that they are very, very bad health-wise. They're also very bad for the environment. When I first started as a chemist a long time ago, carbon tetrachloride here in the center, where you have 1 carbon with 4 chlorines, that was the solvent of choice for organic compounds. When I was cleaning up in lab as a student, I would just like literally take a cloth, soak it in carbon tetrachloride, and just wipe everything down, right? Because carbon tetrachloride cleans up anything that's organic. It is fantastic. It's also a great solvent because everything pretty much dissolves in carbon tetrachloride. Polar things, non-polar things, it's great, but it doesn't react with anything. And so it was the perfect solvent for doing reactions. The only problem is it's also great at destroying the environment. I was just watching the news this week and I heard that, because of this, the COVID-19 going on right now, that people are moving less and that sort of thing. They're already seeing an improvement in the ozone layer. Well, when I was a kid, there was a giant hole in the ozone layer, primarily being caused by carbon tetrachloride. Because as it gets up into the atmosphere, the UV radiation from the sun hits it and turns it into radicals, which breaks up the ozone in the ozone layer. And so it was causing all sorts of problems. Thankfully, the EPA banned its use or made it so that you have to really... I needed it for a reaction a few years ago as part of my research. This is probably 5-6 years ago now. So I ordered some, and I just ordered like a 100 milliliter bottle of it, and it was ridiculously expensive. And about 3 days later, I get this packet in the mail, and I had to fill out a packet of information of how I was going to use each milliliter of it. And then I had to sign saying that for every milliliter I didn't use, I would ship it back to the company. Just the regulations for the use of it are really, really stringent, which is great because if you look at our ozone layer, since it was banned its use was banned in about 96. The ozone layer has just been reforming and is the healthiest it's been, now since the 1940s or 1950s. So its ban was a very, very good thing. One that's not on here that you might hear something about is trichlor. It's a carbon-carbon double bond with 3 chlorines on it. And this is one of the compounds used in dry cleaning. It's actually the solvent used in dry cleaning. It's great because it's polar, and so it attacks a lot of stuff, but it's also got it's organic, so it dissolves a lot of organic materials. The only problem with trichlor is it is carcinogenic and can be teratogenic, meaning it causes birth defects. And so that's why one of those regulations is out there that you should, if you're pregnant or could become pregnant, you really should avoid wearing dry cleaned clothes. And so a lot of work is being done right now on replacing trichlor as a dry cleaning solvent. Now, the paint solvents are often called thinners as well, because if you have a pigment that's dissolved in an organic solvent, you can add in another one of these solvents or the same solvent to thin it out, all right, to make it runnier. They enhance the mixing of the pigment and binders, all right. The more thinner you add, the easier it's going to be mixed together. They make the paints more fluid, which makes it more spreadable and easier to apply. A lot of times when you get an oil paint, it comes in a squeeze tube, kind of like a small toothpaste tube, and it comes out as a paste. And so you can take that, dissolve in a little bit of turpentine or a little bit of paint thinner and make it into a thin paint, which is a lot easier to control and gives you a much better effect with. Now, after you've painted it on, that solvent is going to evaporate away, and the binder then is going to hold the pigment to the surface. Just to give you an idea of the different types of solvents used in the different types of paintings we've talked about, with the encaustics, the solvent was beeswax. And so that's an organic compound. With frescoes, we used water. Okay. With egg tempera, remember that was the egg yolk that was mixed with water. With watercolor, they used gum arabic, sugar, and then water. With oils painting, remember that's the beginning of the Renaissance era, they used what were known as drying oils. And we'll talk a little bit more about this later, but the drying oils are hydrocarbons that are usually 12 to 18 to 22 carbons in size. All right, we're talking fairly large molecules. And so, since they are large, it takes them a lot longer to evaporate away. All right, and so when you're working with oils or oil paints that have these drying oils in them, you have a lot more working time before the paint actually hardens. With pastels, we've got the pigments dissolved in plant gums, which are dissolved in water. And then later on, you had the oil pastels, where instead of using the plant gums and water, they would use sometimes plant gums, but a couple other different binders, along with the drying oils. And so you could have some or some waxes there to make your oil pastels. And technically, I guess you would call those crayons, or a form of crayons. And then the acrylics are the more modern paints, and they're acrylic polymers as the binder, and they use water as the solvent. Now, just a quick reminder, we're not going to spend a lot of time on this because we've already talked about it, but when we make a solution, which means when we go to make a paint, we're going to mix our solute into our solvent. And one of the big questions we have to think about is how much of each is needed. By mixing different amounts of solute into the solvent, we're going to get different formulations, and those different formulations are going to have different properties. We measure the strength of the solution in two different ways. We can do percent concentration, which is basically the number of parts in 100 parts of the solution. So a 10% solution of sodium chloride would contain 10 grams of sodium chloride in 100 milliliters of solution. All right, and if you're making up a solution, for example, when I was making up the etching solution that we use for the brass tags, I made up a 10% iron chloride solution. So I put in 10 grams of the FeCl3, and I dissolved it in 100 mils of water, and that gave me my 10% solution of it. The other way that we talked about measuring the concentration of something is through molarity. Remember, a mole was 6.626 times 10 to the 23rd of anything, right? It's just a unit. And so molarity is the number of moles of solute you have per liter of solution. So a 1 molar solution of NaCl is going to contain 1 mole of sodium chloride, which would be 58.5 grams, in 1 liter of solution. I hope that gives you an idea then of how paints are formulated and how important the solvent is in the paint formulation.